and rigidity of the hybrid integrated circuit. That's when we were using more compliant lead, the bending moments went down. They didn't, at failure of the Higgs, they didn't go up. And the situation was explained also in the analytical model. So I'll not go into the further detail for that. It's a little bit beyond the scope of the course, but what is important is that analytical modeling is helpful to explain some situations, and I will simply mention a couple of other cases. Could the curvature of an optical glass fiber be different from the curvature of its coating? Because quite often we measure the curvature of the coating if it's a coated fiber, and we make a judgment that the curvature of the fiber inside will be the same, and the answer is not always. Could transfer grooves in the adherence lead to lower interfacial stresses? It was absolutely unclear why they could, and it was explained based on analytical modeling. Could stiffer mid-portions of compliant attachment result in lower thermal stresses? They can, although the common wisdom is that, yeah, if you make the compliant attachment more and more compliant, the thermal induced stresses will always go down. Not true. In a situation, in some cases, you want to use a stiffer mid-portion in more compliant peripheral portions rather than to use compliant everywhere. In this case, if you make the mid-portion a little bit stiffer, the interfacial stress at the end will go down. So that's, in general, as I said, in analytical modeling, the rule is the simpler, the better. And I will quote, I was born in Ukraine, and I'll quote one Ukrainian philosopher, Grigory Skovoroda. Skovoroda means in Ukrainian, by the way, means a pen. But he said, God has created the world in such a way that anything that is true is simple, and everything that is false is complicated. Not really, but almost true. And a good analytical modeling should be simple, should be helpful to experimentalists, and particularly in the situation when you encounter paradoxical situations. Now I'll be talking about the linear response. You know, studying about linear response, I want to say a couple of words about this important approach in general. Linear response is based on linear differential equations. And there's a funny thing, I want to tell you this. It was a story about a man who was seeking something under the lamp post, and during the night time, and it was, of course, under the lamp post, it was a lot of light. So he was looking for something, and a passerby asked him, "What are you looking for?" And he said, "I'm looking for my wallet." And where did you drop it? The person who was looking for it showed that I dropped it very far over there. So why are you seeking it right here? Because light is here. And as funny as it sounds, that's actual explanation, while in many cases people use linear equations, because the mathematical equipment of linear equations is well developed, is complete, everything is absolutely crystal clear, what affects what, what's responsible for what. And if you can bring in the real problem and formulate that in terms that could be formulated by a linear equation, right away you make your life significantly simpler. Is it true that it's always the case in the real life? Quite often, no, as it is this example with this fellow who was looking for his wallet under the lamppost. But the Murphy's law in many cases doesn't work, and in many cases you can get away with a linear solution. I'll say even more. To obtain a linear solution is always a prerequisite for obtaining on its basis, when necessary, a nonlinear solution. At the same time, nonlinear solutions in many cases are absolutely indispensable and should be used. But another shortcoming of the linear solution is if you use a linear solution, it's not always clear to what extent it's applicable. Therefore, you quite often, either you verify that experimentally, and if it agrees and we are happy, that's fine. In other case, you can check on the linear model by another model, a nonlinear model, and to understand to what extent a linear model is applicable to a certain situation. And these situations are very different from case to case. In the linear response, I will cover, and I will read it simply the items that I'll cover. A single degree of freedom system subjected to harmonic excitation, and I'll explain some physics of that. Single degree of freedom system subjected to an arbitrary excitation, and it's called a Duhamel integral, but I'm not sure I will show it here, but I'll explain what it is. By the way, in my book, Applied Probability for Engineers and Scientists, there is a lot of information about mechanical behavior or dynamic response of linear systems. So those who are interested can take it and take a look at it. And there are, of course, abundance of literature, excellent literature on dynamic response of linear systems to shocks and vibrations. I'll talk about impact loading and its effect and the effect of viscous damping. Heavy electronic components, reinforced vibrations, random vibrations, in the maximum acceleration, always inadequate reliability criterion. Could shock tests be adequately mimicked could adequately mimic drop tests, or could drop tests be adequately mimicked by shock tests? Could an impact load of finite duration be substituted by instantaneous impulse? Then a compliant surface mount device, printed circuit board interfaces, in other words, compliant interfaces for SMD PCB assemblies, and their role in the dynamic response of such an assembly to a shock load or a drop load, effect of the initial position of portable device on the possible damage of the integrated circuit as a result of a drop impact, and thin and elongated portable devices experiences drop impact applied to the ends, and a printed circuit board with a concentration lump mass at its center, predicted frequency and coordinate functions. And now I will start with each of these particular tasks separately. Now, the way that you will see that in this course, I will address particular, specific, down-to-earth problems that just happened, I encountered with during my long professional life at Bell Labs, then in two universities that I'm affiliated with, in two startup companies in Silicon Valley, where I was vice president of reliability, materials, and packaging. None of these startups exist anymore, but I hope not because I was vice president of these companies. But it's a fact that everyone knows that 9 out of 10 startups don't survive, and primarily because of reliability, by the way, but also because of some obvious business-related reasons. And all these problems were actually actual problems, but in order to understand the physics of these problems, I'll say a couple of general words about linear vibrations. First, let's take a look at this view graph. What you see here, it is a single degree of freedom system subjected to harmonic excitation loading. It's called harmonic oscillator. If you look at the left-hand side picture, it has the models that reflect the mass, which is the box at the bottom, Then there's a spring that mimics the restoring forces with a spring constant. And there is a pot which mimics the effect of viscous resistance, viscosity, and the viscosity-related dissipation, if any. And this is, as far as dissipation is concerned, it's the most, I would say, not an exact science, but people also, they try to go further, then I'll come back, to use this type of viscosity to be able to come up with a linear equation. And you see the equation of motion here is the first term is the mass of the system times the acceleration. And if you multiply the mass by acceleration in accordance with Newton's second law, you have an inertia force, you have a force. The second term is that what I've just spoke about. Is a viscous damping, which is proportional to the velocity of vibrations, and R is the resistance, dissipation. And the last term is the restoring force, where K is a spring constant and X is the displacement. So X is the displacement, X with the dot is a derivative with respect to the time of the displacement, which is velocity, and X with two dots is acceleration. So that's why people use, at least the first useful approximation, viscous damping, because in many cases reflects the actual situation, but most importantly that it helps you to come up with the differential equation, linear differential equation, and based on that to understand the physics of what's going on. In many cases, you have to consider that might not be x with a dot, but x with a dot squared. That will make the equation nonlinear. But in many cases, again, before you want to obtain a solution to a nonlinear equation, you want to solve first a linear equation, and then based on that to make the second step forward and come up with a second approximation. Now, on the right-hand side of this equation, you have the excitation force. In this case, when you have a very typical widely spread situation in outside electronics, but inside electronics as well, when, for instance, when the contour of a printed circuit board is subjected to vibrations, and that will happen when the printed circuit board is installed in a car, in an aircraft, in a missile, or wherever. So in this formula, in this excitation force, the right-hand side of this equation, F is the force, lambda is the frequency of excitation, and T is time, and epsilon is the initial phase, because the lambda T plus epsilon is called phase. And if T is equal to 0, the phase will be equal to epsilon, which is the initial phase. So this is the main players in this equation, which is the equation of for a single degree of freedom system, like a mass supported by a spring, and the role of a spring is reflected with the third term of the left part of the equation, and also has a viscous damping, which is the second term in the equation, and the mass itself experiences a certain acceleration, and the product of the mass and acceleration are the inertia forces. And in addition to that, we have also the excitation forces on the right-hand side. In the so-called D'Alembert's principle in dynamics that says that the sum of all these forces, including inertia forces, should be zero. From static, we know that equation of equilibrium requires the sum of all the forces should be zero, but the inertia force is a special, peculiar type of a force. It's not an external force, it's an internal force, and therefore it was actually not obvious that, generally speaking, you can apply the same principle of equilibrium to this equation. Now, what people typically do, if you'll see another equation under this first equation on the left-hand side, the second line, is you obtain when you divide both parts of the equation on the mass. And in this case, you obtain the second equation, which is x with 2 dots plus 2r. It's more convenient to deal with 2 r's, x with the dot, plus omega squared x times, it's clear what you have on the right-hand side. The important thing that square root of the k divided by m has a very important fundamental physical meaning. It's the frequency of free vibrations. Why it's called the frequency of free vibrations? If the right part of this equation is put equal to 0, in this case you have free vibrations, which are vibrations without an excitation force. Or you can interpret it physically that excitation force was some, and at a certain moment of time it was removed, but the system will still continue vibrating until, because it has a dissipation term r, the equations will fade out. But omega, which is square root of the spring constant k divided by mass m, it's frequency of free vibrations. We should try to remember that because it will be a very important characteristic. On the other hand, the resistance dissipation can be obtained as dissipation force r divided by 2m. 2 is simply its mathematical trick that makes the equation, the solution to this equation more convenient and simpler. So what I'm saying here is a single degree of freedom system is such whose position is determined by the value of just one parameter, generalized coordinate x. And examples are the position of a mathematical pendulum is determined by the angle of its deviation from the state of equilibrium. What it is, okay, let me show it here. This is a mathematical pendulum, and it's when it rotates or vibrates with respect to this position of equilibrium, this angle can be used, and it will be just, this was a linear coordinate, this will be an angular coordinate. The other example here, for instance, it can be the position, the other example is the position of a mass constrained to translational motion in the given direction is determined by the distance of this mass from the initial reference. And that's exactly true for that example that you see on the view graph. For instance, you have a mass, this you have here, at the initial position it was here, then it moves here, let's say, and then it will move here. And this deviation is x, also a single degree of freedom system, exactly described by the equation that you see here. Or the position of a rotating disk is determined by its angular coordinate, same thing. The analysis of the dynamic response of many structural elements, electronic and photonic components, experiencing shock and vibration during when subjected to different type of loading, can be simplified if these elements are treated as single degree of freedom systems. In our analyses that you will see later on today about nonlinear systems, there is even a strong, a significant reason, a well-substantiated reason why we can successfully restrict our analysis to the first degree of freedom only. And in this case, although a printed circuit board or a wire band is in effect a multi-degree of freedom system, we can effectively and successfully in practical applications to restrict the analysis to the single degree of freedom system and get away with a reasonably simple solution. And here I will want about a couple of words about resonant curves. I want to show you that I skipped deliberately, let me go back, this picture on your right-hand side because I have it again here, and I will describe it. So what you see, I call it resonance curves, although not all the curves here are resonant conditions, but we want to understand what brings to resonant conditions. On the left-hand side, you see the same thing. The only difference is here, and I did that on purpose, I didn't indicate any dissipation. In the simplest case, and as Einstein was telling us, a model should be as simple as possible, but not a single bit simpler. So two forces are absolutely crucial to understand what happens. It's the inertia forces, therefore we have a mass here, and the restoring force, therefore we have a spring here. We don't have an excitation force here, we don't have a dissipation force here. So this model is still meaningful, and this is fundamental for understanding the physics of linear vibrations. On the right-hand side, on these plots, you see on the horizontal axis, you see the ratio of the frequency of excitation to the natural frequency of vibrations. And on the left-hand side, you see the amplitude of vibrations, assuming that you do have a external force, but of a single unit, of a unit amplitude. And let's look at a couple of typical curves here. And here, by the way, you have on the right-hand side, you have also the principal system on the left-hand side doesn't have excitations nor viscosities. But on the right-hand side, we show how this system behaves, performs, when you have also all the four types of system. Let's start from the left-hand side. In the left-hand side, because on the horizontal axis, it's the ratio of the frequency of external excitation to the frequency of free vibrations. On the left-hand side, when the frequency of the external excitations is 0, you certainly have 0. And in this case, of course, the response will be static. That's why everything starts from 1. And the amplitude is equal to the excitations, or external force is 1. On the other hand, on the other right-hand side, you have the frequency, either the natural frequency is significant, or the frequency of external excitation is low. And in this case, on the right-hand side, the situations, you have very low amplitudes. Now, the worst situation, that's why it's called a resonance curve, when the frequency of excitation and the frequency of natural vibrations are close. In a situation when there is no dissipation at all, when they're equal to each other. In a situation where there is dissipation, they are a little bit different, but not very much different. Again, I want to indicate that, that when we have a relatively low viscosity, in this case, people can get away without considering the effect of the low viscosity on the frequency of vibrations, because the frequency of vibrations with viscosity can be calculated as the frequency of vibrations without any viscosity minus that parameter r that I indicated. Here you see on the lower left corner, it's lowercase r, that's exactly this r. And if the frequency of natural vibrations without viscosity is high, the role of viscosity, the viscosity is relatively small. In this case, you can neglect the second term, and in this case, the natural frequency of natural vibrations with viscosity, consideration of viscosity, will not be very much different of the frequency of natural vibrations without considering the viscosity. However, as you can see from this formula, when the viscosity is, this parameter is significant and approaches to the natural frequency of vibrations without any viscosity, it will result in the fact that the frequency of vibrations with viscosity will be next to zero. Zero, that means that no vibration may possibly occur. And that's what you will see on this resonant curve when you see these lines that do not exhibit any resonant condition. They go from unity down to zero. But the resonant situation is where you have either one ratio, one or close to one. And in this case, you have peaks on these curves. In a situation when you don't have any dissipation at all, the amplitude of vibration is infinitely high. Let me tell you this. This is a situation, this is nonlinear theory. And we will make a break in about 5 minutes when it will be appropriate.
You're already 5 minutes long.
Okay, let's make a break.